So let's have a look at this problem. It's also going to be a problem for the Pearson's chi-square test. And so let's have a look. Researchers randomly assigned 304 subjects from a population with insulin-dependent diabetes. So all of our population is only those are insulin-dependent, to 4 treatment dosages for a new drug to manage their glucose levels. The hope is that this new drug will lessen their dependence on insulin. So after the treatment period, they classify the subjects as having had to use less insulin than before, no change in their use of insulin, or they actually had to use more insulin. So the researchers want to test the claim that there's an association between the treatment dosage and the change in insulin use. So there are 4 different dosage groups: the low dose, medium dose, high dose, and very high dose of this test drug, and there are 3 categories for the outcome variable, so our disease variable. In other words, there'll be less insulin, no change in the insulin usage, and more insulin. And so we see the joint frequencies there. And so I won't read them all out. You can see them on the screen. And then we have to use a Pearson's chi-square test to determine if there is an association between the dosage and the change in insulin usage at the 5% level of significance. So can we do that? I think yes, we can. So let's do step number 1. And that is going to be, what are all our parameters, population parameters of interest? So our population parameters of interest, those are really going to be all our joint probabilities. You can see that there's 1, 2, 3 times 4, there's 12 of these joint probabilities. So we're actually looking at each one of them, the probability of a low dose group and less insulin, the probability of a medium dose group and less insulin. So you can really describe all of them, which will take a long time, but at least try and list all of them for me. Now, this is a video, and don't want to waste your time, so I'm just going to put ... You can fill in all of these there's 12 actually, 12 joint probabilities. And so let's have a look at step number 2. We just want the null and the alternative hypothesis. So this is easy to state. We're just going to say that the treatment dosage and let's say change in insulin use, that's terrible, insulin use is not associated. And the alternative hypothesis would be that these two, I'm just going to say, are associated. But please, you know that you have to write all this out, that the treatment dosage and change in insulin is associated. Great stuff. Step number 3, very easy. Our alpha value is going to be 0.05. We were instructed with that. Step number 4, what test are we going to use? Well, we're going to use the chi-square test for association, also known as the chi-square test for independence or Pearson's chi-square test. Now we have to look at what's going on here. This was our contingency table, or our table of observed data. And so remember, this would be O sub 1, O sub 1, 2, O sub 1, 3. Let's write all of them out. 2, 1. 3, 1, 4, 1, row 2, column 2, row 3, column 2, row 4, column 2, and then row 2, column 3, row 2, column 4, row 2, column 1, 1, 2, 3. Row 4, that's terrible. Row 4, column 3. So that should also be, which is fix this one. This is row 1, 2, 3, column 1, 2, 3. That was terrible. Okay, row 3. Can you see that? Let's say 3, 3, row 3, column 3. You know what I'm talking about. So let's do our expected values. Our expected values under the null hypothesis. And remember, we need 80% of them to be 5 or more. And you do remember how to do these. If that's my observed row 1, column 1, I take its row total, 66, times its column total, 131, divided by 304. So you just look at that row total, that column total, and divide it by that. So this one I'll just write it all out. So that's going to be 66. Let's change that. 66 times row total, column total, 131, sum total, 304. Okay, so that's going to be expected 1, 1. Let's put that in orange. It's going to be expected row 1, column 1. Let's do expected row 1, column 2. So if I look at that 33, its row total is 66 times its column total is 133 divided by the sum total, which is 304. And I'm going to go through all of those. Now, I'm just going to write them out quickly for us here. That's the wrong color. Let's do expected 1, 1, expected 1, 2, expected 1, 3. And there you go. Those are all my expected value. Remember, whichever one we're talking about, if we're talking about row 3, column 2, so that 34, it will be 87 times 133 divided by 304. And there's my expected values, and you can see they are all at least 5. So I need 80% of them to be at least 5, but they're all more than that, so that is no problem. So what we're going to have is a chi-square test for proportions. All we still need to calculate is what is our degrees of freedom going to be. Remember, that is just the number of rows minus 1 or the number of columns minus 1. And by number of rows, I mean how many categories in this variable, how many categories in that variable. And if we work that out, our degrees of freedom is going to be, well, that's 1, 2, 3, 4. So 4 minus 1 times 3 minus 1. And so that equals just 3 times 2, and that equals 6. So 6 degrees of freedom. And we're going to have x squared is described by the chi-squared distribution on 6 degrees of freedom under the null hypothesis. So I just want to put step number 6, I just want to squeeze it in here, because what you will have to do is the following. Let's have a look. Get the right pen. Remember our x squared statistic. X squared is going to be the sum over I equals 1 to the number of rows. Sum over j equals 1 to the number of columns of Oj minus E sub ij squared divided by Eij. That just means we're going to go through all the rows, column 1, column 2, column 3, then jump to the next row. Row 1, column 1, column 1, column 2, column 3, column 1, column 2, column 3, column 1, column 2. And I just have to take observed 22 minus expected 28.44. So let me write that first one out. And so that's going to be the following. That is going to be equals. So let's start with the first one. I observed 22. What did I expect? Minus 28.44. I square that and I divide by that exact same expected, 28.44. I'm going to move on to the next one. I observe 33 minus I expect 28.87. I square that and I divide by what I expect, 28.87. And I'm going to go to all these 12. Next one, next one, next one, next one, next one. All 12 of them. And in the end, check with your calculator. I'm just going to jump ahead. I get 6.43. If I look at all of those, if I add all 12 terms, I get to 6.43. Now for our critical value, step number 6, I want the critical value. Now that critical value is going to be on alpha. So that is going to be 1 minus alpha, and it's going to be on nu, my degrees of freedom. So that's on 0.95 and 6 degree of freedom. And when I plug that into my spreadsheet software, I get a value of 12.59. And we see that our chi-squared statistic is not more than this critical value. And we fail to reject the null hypothesis. Fail, say, to reject. Oh, my writing is horrible today. So step number 7, we're going to say, so I've written there's not enough evidence in the data at the 5% level of significance to show that dosage and insulin use are associated with each other. So if this was a real experiment, we'd say that, that it's of no use to use this drug at any one of these doses, because dosage, if you just look at dosage and you look at the change in insulin, these two things are not associated with each other. So at least we could say that, that a change in this dosage is not going to influence whether you use less insulin, no change in your insulin, or more insulin. That these two things are not associated. Dosage is not associated with this change in insulin level. ChatGPT, I'm using ChatGPT 03 Mini High. I've pasted my problem as we've had into this first prompt. Once again, I do note that I do use the dollar symbols so that I can use LaTeX or LaTeX mathematical typesetting. So that would render as chi-squared. And if you want to put in equations such as this, ChatGPT is very good in understanding LaTeX or LaTeX. Leave a comment in the description down below if you want to learn more about mathematical typesetting. So if you do have equations, it's very difficult to write an equation in a prompt in words, but you can use this mathematical typesetting to do this. So I've also said generate a solution to this problem following our 7 steps. So let's have a look. Our population parameters of interest there, it's stated it there. You can have a look. The null and alternative hypothesis that these two variables are associated and they are not associated under the alternative hypothesis. Level of significance is 5%. Great. We're going to use a Pearson's chi-squared test. We see that we have independence. The expected frequencies we still have to work out. They should ideally be at least 5. And we have random. It's created a nice contingency table for us. It's reminded us that it's always row total times column total divided by what it calls grand total, what I call sum total. Same thing. And so if I look at this 22 here in cell E sub 11, that will be 66. It's its row total times 131. It's column total divided by 304. It's column total, so I would expect, I observe 22. But under the null, I would expect 28.44. And I would do that for all 12 of the cells. You can pause there and you can see all the values that ChatGPT did. And I think that's pretty much the same as what we did. And now it's just going to go through observed minus expected squared divided by expected for all 12 terms, all 12 cells. And eventually you can pause the video and have a look at that. And eventually we get a chi-square or an x squared test statistic. It uses the chi symbol there. We like to use the x squared statistic, and we said it follows a chi-square distribution. But in any way, the value is 6.43. For the degrees of freedom, it's the number of rows minus 1 times the number of columns minus 1. So 4 minus 1 times 3 minus 1, that's 3 times 2 is 6. So that's cool. That gives us a critical value of 12.59. And clearly our test statistic 6.43 is not larger than 12.59. So we failed to reject the null hypothesis. You can read the conclusion there. I think that's pretty good. And then I said, ChatGPT, please create some code for to visualize this problem. There is the code that it wrote. I'm going to say copy. I've pasted that code here into Google Colab Notebook. Remember, these Colab notebooks are available in your Google Drive. Just as you say new Google Sheet or new Google Doc, there's also new. When you go under more, you should find Google Colab. If not, you can always just install it as an extension in Google Chrome. And there we go. We see a chi-square distribution on 6 degrees of freedom. Looks a bit different from one on a single degree of freedom. There's our test statistic at about 12, or our critical value at 12.59. And this black dotted line, so you see this region of rejection, that's 5% of the area under the curve. So all these x squared values on the horizontal axis, they're all possible under the null hypothesis. But we get one here that's in the 95% most common ones. And so we failed to reject the null hypothesis.